Hi everyone, good morning. Welcome to this week 8-1 session of system design. Today we have Ajay Tanikonda volunteering to present Cassandra deep dive. So yeah, if you'd like to be part of future sessions to be a presenter or volunteer, please ping me in Discord or like after this session. Yeah, so Ajay, let's get started. Over to you.
Thanks, Naka. Hey guys, this may not be a complete deep dive, but I'm not going at a tree structure level or a structure level at which the Cassandra lives, but I'm trying to cover as much width that we can at a high level with respect to how things work. Let's go through what are the key concepts that we're trying to cover here. One is, how does Cassandra fall into the CAP theorem, and how does it implement consistency hashing? What are the replication strategies that they use? How are the consistency levels defined? How is the write path, read path, and what is the concept of compaction that consistency that Cassandra is using, and what is gossip protocol? This is what the agenda that I'm trying to cover today. Feel free to chime in between. I'm not an expert at Cassandra, or I don't have much hands-on as well. I just learned it and thought of presenting that based on my learnings. So please feel free to chime in between if I do a mistake, or if you feel something is not right. Thanks for that. Let's move on. So the first thing that we are looking at is the CAP theorem. So Cassandra falls into the bucket of having availability and partition tolerance.
So Ajay, do you want to give a brief overview of Captum before jumping into what Cassandra supports?
Yeah. So as of today, if you see how CAP theorem works, or what is CAP theorem means. So given any kind of system, so it is impossible to have both consistency and high availability while having a network partition. So that particular concept of so if you take 4 nodes, I'm sorry, to take kind of, if you have 1, 2, 3, and 4 nodes in here, and if you're talking about data being available and data being consistent across all 4 nodes, and also data being so we being able to partition this data in between, that state of occurrence is like the most ideal state, which falls into this circle. So this is the magical state that we are talking about, which is quite impossible to achieve as of today, I would say. And Cassandra, for that matter, has multiple nodes allocated. And let's say you have 4 nodes like what I'm showing here, and you have a write request that is coming in, which you're writing to one of the 2 nodes. So these 2 get updated, and then you have 2 more nodes which are not updated, which means you're not being consistent to the request that you're providing. So that fails the consistency, and that gives you availability and partition tolerance. While certain set of nodes in a group of nodes can only adhere to one response, and the others are not able to adhere to another the same response. It falls into a bucket of eventual consistency, where that request comes and served by the other nodes eventually after a certain point of time. So that's what we are trying to cover. So if we take this same system being ideal and serving all the nodes, serving all the requests in a consistent manner, which means when you write to node 1, your response is made sure that it is written to all the other 4 nodes and only then the requests are served. So in that case, what happens is when you're writing to node 1, if it is not reflected in node 3, in the meantime, if you come back and ask node 3, it will not respond to you with any response. To make it consistent and partition tolerant, which means you're basically giving up your availability at that point. So this is a CP theorem. So generally, what happens with the relational world is you make it you make sure that your data is written to all your replicas and only then you respond. It again depends on how you set your system isolation levels, etc. Let's not go that deep into that piece, but yeah, that is where I'm talking about Cassandra being more about availability and partition tolerant. Okay, so while there is one clause over here that I want to bring up, there is a flexibility in Cassandra where you can define consistency levels, wherein when you are submitting a query for a write or a read request, you can define a consistency level. We will go there in a subsequent slides, but wherein you can keep the system as a strongly consistent response for a specific query that you're talking about. But having said that, this is not an ideal way of dealing with Cassandra, and this is not a suggested approach where you keep everything as strongly consistent, which increases your latency, because Cassandra is more about scalability across data centers or regions or multiple nodes, and not more about being a strongly consistent system like a relational system. Any questions?
So the levels of consistency, will they be defined initially when you are setting up, or you said you can change them at every, how would we change it at every write request?
At a read or a write request, you can specify the consistency level as a column, or I will go there.
I think he has it in agenda, right? Okay.
Yeah. So I will cover it in detail, but at a query level, you can specify what kind of consistency that you're expecting out of that query. Okay. So let's move on. So basically, we are talking about Cassandra as a distributed database, which implies your data is partitioned into multiple nodes across, and then this system would be serving you the requests based on various node response. Okay, and then having said that, that brings up a linear scalability to Cassandra, wherein when you increase Cassandra's capacity or scalability can be increased by simply adding new nodes, and it can scale horizontally, meaning you can increase number of data centers or the number of nodes within the Cassandra cluster, which automatically increases its response times, improves its the scale at which it can grow will be improved. So an example over here would be like if you take Spotify, okay, it serves globally across various places using multiple Cassandra nodes across the clusters, whereas all its data is distributed globally, while the nodes are multiple clusters of Cassandra or a large set of clusters of Cassandra. As the data grows, the number of nodes grow, and the serving capability increases over there. So when I say multi-cloud or multi-data center, this is the beauty of Cassandra that it brings in, wherein you can set, so a cluster of Cassandra can span across multiple data centers, and multiple clusters of Cassandra can serve your purpose as well, which implies you can define a replication strategy wherein your requests are served from multiple data centers based on what kind of consistency level that we are requesting at. Someone is saying something.
No, I think you can continue, Ajay. I think it was.
Okay. So, having said that, Cassandra, in general, we might have seen this picture quite a lot. So it is having multiple nodes in a ring, and we are looking at data that is coming in, wherein the data is defined with a partition key on it. So how does this partition key work along with multiple nodes on Cassandra is what I'm trying to bring over here. So if you see that same data is passed through something called a partitioner, which is a hashing function that we are talking about, which provides token values for that partition key. And based on the token values that are being derived, you see the last two values, Berlin and Nuremberg, they are distributed into one specific node based on what we are getting over here. So these two values are meant to a specific node. So the partitioner is basically, we use hashing functions. Like, if I just want to bring up what is hashing and how does that work in a real world. So hashing is basically, you can hash any digital content in the system, right? So basically a digital content is nothing but zeros and ones. So hashing functions are generally, you will be randomizing the order of the binary values of that particular digital content, so that the hashing function will provide you. So if you pass, so let's say you're having H1 and you pass 1, and probably you will randomize the system, and then your hashing function will provide you some value like 10. So there might be one more hashing function which might give you that same binary digits being randomized, and your output might be getting to be 20. So there can be multiple hashing functions that can provide you different values out of based on the input, and that will be consistent. Whenever you pass this one value to H1, it will always be 10, whereas H2 will always be 20 for that same value. So whenever that same value comes in, so when D is coming in, it is always deriving it to 45, and it is ending up on a specific node. So there are usually two major partitioners that they define. One is Murmur-3 and other one is MD5. So Murmur-3 and MD5 are the hashing algorithms in mathematical terms, which are similar to whatever I'm talking about, the randomizing binary values underneath, and then providing you a consistent value as an output for an input value. You cannot reverse these functions, but these are basic core of hashing that we are talking about. So let me go to, so there are previously they were having random partitions or byte ordered partitions. They are even supported for backward compatibility in Cassandra, and these partitioning functions can be defined in YAML file on what kind of configuration that we want to use in order to distribute our data. So let's look at what is a hash ring before jumping on to how the data is, going into more details of how the data is distributed. Hash ring is something where you are not having any master. So that's another major factor of Cassandra being so much scalable and being such a big hit. So the hash ring is something where you're having a data range defined between the two nodes and getting distributed without any master slave architecture. and there are no zookeepers or anything which are controlling the data, while there is something called gossip protocol, which will be followed by these nodes in order to make sure the state of the nodes is appropriate and the data is appropriately served or written to the system. I'll go to gossip protocol at the end. Let's hold that thought for now. There is something called replication factor, wherein you're talking about data being replicated on n number of servers. So if your replication factor is 2, that means when a write request comes in, it writes two copies of nodes, and it serves the request based on those 2 copies. So yeah, every single node in Cassandra holds data. It's not like it's a master node, it doesn't have any data or it doesn't serve any purpose. It just stays for coordination. There is no such node in Cassandra ring that only serves the request rather than reads and writes. So the data location on the ring is always determined by the partition key. So this is where the concept of partition key comes in, wherein it is mandatory for you when you are defining your table. It is always mandatory that you provide a partition key. If you don't provide a partition key, it takes your primary key as a partition key. If you provide a partition key, it takes that particular thing. Any questions?
So this hashing is, I mean, like in other words, called consistent hashing, right?
Yeah, I'm coming there.
Oh, you are going there.
Yeah.
Okay.
Yeah, exactly.
So then
I'm just briefing on how
this.
it is distributed. So yeah.
Okay, let's take some questions.
So can the partition key be multiple keys? Let's say that we have a composite primary key, right? We wanted to give it 3 or 4 keys. So how does it is really, does it do, because the data can vary in different data types, right? On the column. So does it applies on, basically my question is, does the algorithm takes care of, basically it has to come to a single value, right?
So basically you're talking about, so any number of columns in a given order will always derive to a specific hash value, right?
Right, yeah.
So it is all about how you hash your value and how you get your output out of the combination of columns instead of a single one.
Okay, and that is something we have to do, or Cassandra, like whenever we define the
so when you define your table creation, you will have something called like in so
you will pick some partition key. Basically, it could be customer ID or something, whatever it is. So you internally distribute based on it.
Right. So when you define your table, you will define like in relational, you will define a primary key like on the table. If you don't want your primary, so if you want your partition key to be a clustered value, then you will use braces. I'm not covering the syntaxes over here, but that's pretty straightforward actually.
Okay.
Yeah. Can I pitch in some points about this?
Sure.
Okay. So Cassandra is it's basically defined as a key distributed key value store, right? So when you design a key space, that means a table over in Cassandra. So you can give any number of the column values as partition key. Like you said, multiple columns can be given. So these columns are clustered together as key, and the values are the column values. Maybe I can ping an example of how something would look like.
Yeah, sounds good.
Ajay, I had a question.
Okay.
Between the point 4 and 5, so is the data gets replicated to only a certain number of servers, because the point 5 says that all nodes can handle read and write? So can you please elaborate on that, sir?
So when I say all nodes hold data, that means, so in your, let's say you have a zookeeper system kind of thing. Zookeeper will never serve you any data, or it doesn't contain any data, right? So it eventually routes your request to a specific server. I'm just quoting an example over there. But in Cassandra, when a request comes in, it goes to something called a coordinator node. Like, let's say you have this as your coordinator node. So your request is coming in. I'll go to the read path and stuff like that. But let's say this is your coordinator node where your read request is coming in. So what this does is, this request will have, so the coordinator will know which, so let's say this is asking for 25. Sorry. This is asking for 25. So the request comes here, and then it knows that this data range is pointing to this particular thing. So it actually redirects your request to this. That doesn't mean that this node is not having any data. It has its own range, but this is picked as your local coordinator. So your driver that you're defining will point to that particular coordinator, and it reroutes to this thing. It doesn't mean this is always your coordinator. Any of the nodes in a ring can act like a coordinator. That's the point of having, it will have both reads and writes, and it holds the data. Every node holds the data, it has reads and writes, and every node is aware of the partition key token ranges. So the request will be routed to respective nodes and its replicas. If you have a replica of this in another node, it will have two types of requests. One is data request and other one is digest request. So the data request is something that serves you the purpose, and digest request is something that makes sure that the data is consistent between the nodes. So I will come there. We can talk more about it, but did it answer your question?
Yes, Ajay, perfectly.
Okay, thank you.
One question on the same terms. I'm not sure if you are covering it in the later section. So when a request comes in, it comes in for a key, right? Like primary key. But the way is stored is all based on the partition keys, right? So there should be some link between like the key that you got in and linking to the partition key, because they could be completely different, right? These two, the default is same.
No. It is always, so in Cassandra, it cannot serve you a request without having partition key in the query. So it is always the way. So the way that you design Cassandra system is, so if you have, let's say you have table X, you have column X, column and Y1, Y2, Y3. Okay. So X is your partition key. That means in all your queries, you are making sure that X is part of it. Let's say you have another query that wherein your Y1 becomes your primary. You don't have X as part of that query. Then you need to make sure there is one more column family that you're creating with Y1 as your partition key, and X, Y2, Y3 are just part of that column family. So this is another set of column families that you are addressing, wherein that request will be served based on the second column family that you're defining. So which column family, in the sense, you're talking about two different tables in a regular terminology. So this one is CUF1, this is CF2. The first request having partition key of X will be served with first column family. Second request will be served with the second column family.
Interesting. Well, like I thought the problem of designing what partition keys to use is to make the replication factor things, right? And now we are putting that burden on the caller also to make sure he understands what partition keys are.
Yeah. So maybe I can answer this one. So if you see the chat that I pinged in, so as I said, Cassandra has a key value pair. So in Cassandra's query, you should always the where clause is very important there. you should always include your partition or clustering key over there. So this is to say that so it's like think of an hash map. Like without knowing the key, how can you search for a value?
Right.
So your var class should either should contain the your primary key. That means if you have multiple clustering primary key, like 2 or 3 columns, your var class should have all the primary keys mentioned. Otherwise, you will the query will return error.
Okay.
Yeah, I think let's cover a little more so that we can understand what we are talking about, because underlying storage structure will give you more clarity on how this is actually working.
Yeah.
I mean, this is more hard-bound definition that Cassandra is meant to be a key value kind of system, like someone is mentioning just now. It's not like a regular RDBMS system where you first data model your system, design your dimensions, load your facts, and then go for, okay, I'm getting XYZ queries, so I will create n number of indices, so that will serve my purpose. So that is your regular relational system design, right?
Yeah.
Whereas in a NoSQL system, what happens is you will first identify what is your use case, what are your queries, and then you model your system based on the list of queries that you're getting. In general, I'm not generalizing this to MongoDB or any other system, but NoSQLs are generally meant for most of the prominent NoSQLs are generally meant for designing your use case first and then going backward. Okay, now I need this system to be designed in this particular pattern.
Yeah, interesting. I mean, like I was thinking, like the use cases can keep changing and enhance and all those things.
Yes.
Right?
I mean, Cassandra is definitely not an easy system to maintain in those terms. If you have a very dynamic range of queries that you want to serve, then this may not be your ideal system. But if you want to scale your system based on the needs, and it is always easy to add a new column family and all, but I don't say this will serve all your ideal purposes.
Oh, cool. Makes sense. Thank you.
Now let's see how the consistent hashing works. So there is a concept called vnodes. So I'm talking about, in a data ring, I'm talking about the ranges, right? Here I said this range is 1 to 25, 26 to 50, 51 to something, and 76. If this is how you are designing your system, what happens here is, let's say you have a range of 1 to 25, 25 to 50. And this part is having 50 to 100, right? So most of your requests that are falling in this range will always go to one single node, right? Because it is always a clockwise request adherence. So in that case, your load on your one node will always be very high. And even when you add, let's say your node increased, even when you add a new node over here, so when you are bringing up this node, or the way that you load the new node that is added is you will put a bunch of load onto this in order to read all this data over here as a new set of partitions that you are adding. So this is not how this system can work, right? Because you will bring down this system one day based on some imbalanced partitioning. So the way this problem is solved in Cassandra is by using consistent hashing. I was talking about hashing earlier, right? So what is happening with hashing is, let's say you're given H1, H2, H3. So if you use just one function, so you have two things, right? Whenever you are talking about hashing and load balancing as a combination, you're talking about request ID and you're talking about server ID. I'm talking in general terms. I'm not talking in terms of how Cassandra works. but I'm talking in general terms how consistent hashing works. So you have something called request ID and server ID. So if you just go by request ID hashing with one function and say, okay, I'm passing request ID 1 and I get something called 10, then your request will go to be served by this particular node. So this is always how this request goes to one single node, and then it is served, it will be serving the purpose. So that is where this issue of having nodes being very heavily loaded with the imbalance comes in. So the way that is solved is, if you have the same value being passed through multiple hash functions, okay. So one is giving you a value of 10, other is giving you a value of 20, other is giving you a value of, let's say, one is giving you a 50 and other is giving you 70. Okay. So what is happening is, every time your request comes in, you are not putting everything into one single range, but you're putting it in 3 different buckets. So what will happen here is, your server, so this is your yellow. So let's say you have 3 different values. The first one, let's say, is 10. The second one, let's say, is 30. The third one is 50. And then this is 70. So if you see the requests that are coming, so whatever requests that are coming in, if the request is deriving a value of 10 that goes to this, if it derives a value of 30 also, it goes to this. If it derives a value of 50 also, it goes to this. So your range of scattering the request spreads across the ring based on multiple hash functions that you are using. So your node can serve the purpose in a much scalable fashion. Also, one other thing is, let's say you have a BC node. Okay, you have some 128 GB node which you're bringing in and you're adding it to the same ring. These 4 are of equal nodes and they are serving the data equally. But you want this node to be serving more number of requests because you're putting in a vertical scaling into this, right? So in that case, what they will do is, you will pass it through more number of hash functions. Like, you may be passing it from H1 to H9 and distributing on the hash ring, which means your server might be having multiple places where it can be serving your purpose, which is more than the other nodes, right? That is one advantage of using this. And other one is, when you bring down this node, you're talking about having multiple places addressing the failure, and also you're talking about the data being distributed across multiple servers. It's not like, okay, here you're saying this is going down, which means it goes to yellow as well as sorry, not yellow, it goes to green, and then here it is going down, it is going to green. Maybe I took a wrong example, but if you understand my concept, when you bring down a server, it doesn't affect one single node all the time. It can affect varying range of servers, and it is distributed even in bringing down or bringing up a new node into the system. Any questions?
I'm sorry, I didn't get clearly this. So when this beefy node goes up, how does that happen? Like, I mean, how do we ensure that other 3 takes the equal load?
No, beefy node, I'm just giving you an example where you can distribute the data, the request on more number of hash functions. So it gets distributed across the hash ring, and it can serve more number of hash values of the request.
In that ring, you can imagine that beefy node will have multiple sections where, like, each of the section is a range of hash values which will be accepted by this beefy node. Basically, this beefy node will have more such hash ranges spread across evenly.
Yeah.
So let's say you have a ring of 1 to 100, right? So let's say you say this is 100. So now you are having only 4 nodes. I mean, not 4 nodes, but this is the range. Now you brought in a beefy node, which is pass it through 9 different functions, which means you're catering that request to 9 different parts on the ring, right? This is part 1, part 2, part 3. So that range of request ID will be served by the node that is associated to that range, right? So when you pass it through multiple hash functions, you're talking about, so if you take this as 100 parts, you're taking 9, let's say 9 parts of it to one specific node. So that is where your vertical scaling comes in, where this is a larger node having more number of ranges associated to it and serving the request to that. Does it make it clear?
Yes, it makes.
So
Okay.
one question. So you said we pass it through multiple hash functions. So let's say each hash function will give some different node, right? So then will we take
Right.
node which has got maximum values and serve the query from there, or how do we serve the query?
No. You are not. So this is how you distribute your ring, right? Your request will always give you only one output. So what is happening here is, for your request, you will always get a value of 10, which means so this particular thing will be served on your ring based on where it is falling. So, but how you distribute your underlying nodes is how this ring works. You got my point?
So
This is not.
So what is the use of multiple hash functions? Why didn't I use one? So you are saying we got a value of 10 from
So
the hash.
if you have only, so let's say you have only one hash function, okay? So for your node, you have one hash function, which means your node will only serve one purpose of one range of values, which means in this picture, this is only using one hash function. So whenever your hash function responds in this particular range, this is giving it to this particular node, right? So only the requests that are coming in this particular range is coming to one node. Whereas if you use the concept of V nodes, you're talking about this, the distribution of hashes are based on virtual nodes. So one node can have up to 128 virtual nodes. So each virtual node will have one particular range. So each virtual node will have one function associated to this. Okay. So your node will be serving multiple V nodes, which are distributed on the hash ring. And the V node value or token value will be mapped to your request hash.
Okay.
You're clear?
Yeah.
Sorry, I scribbled the entire thing. I made it more confusing, but I hope I delivered the message.
Yeah. So let me add.
Yeah.
So let's say we let me try to explain what I have understood. So let's say we don't have any consistent hashing and we are using a typical round robin method to distribute the load. So in the typical manner, what would happen is, like, if we add or change any nodes, then all our hash function will be changed. So like all the requests will get started to serve different servers. Let's say request 1 was served from request 5, and if we add one or more, if we change to the number of nodes, then request 1 may serve to node 2 or 3. So what will happen in consistent hashing is like we would just remove the one, we will just change our node. So all our nodes, all the requests will not distorted. I mean, let's say only 80 requests, I mean, sorry, only 20 requests among hundreds will be changed. The remaining 80 requests will be served as the same like they were serving earlier.
Mm-hmm. Yeah,
Yeah, so
that's another point. Yeah. So what I don't know who was talking there, but if you see on a ring, if you're talking about having 4 nodes, and this is serving you 1 to 25, 50, 75, and 100. So when this particular node goes down, all your requests that you're serving here will lose that connectivity, and you need to rehash the whole set of values that you're defining here, because you only have 3 nodes now, and your hashing output cannot be distributed according to your 4 node structure, right? So when you do a hash value, you cannot, so you know that modulo way of distributing data, right? So you got a request ID. So let's say you have a request ID 1, and then you hashed it, that request ID to 10, okay? And you distribute this data based on some modulus operator. So you say 10 mod 2, 10 mod, let's say 4. So because you have 4 nodes, 10 mod 4 is 2. So what happens is it takes that request ID, it calculates this value, and then it goes to the node 2 and serves the purpose. Now, if you bring down this node, you should always make sure that your modulus that you're applying is now 3 and it's not 4. So you should always revisit your calculation and update your logic of going to which node, right? So that is what he was bringing up. So the next time you have 3 nodes, so what happens is you got a request ID 1 again. So the hash will give you 10, but where your 10 mod 3 will give you 1. So now the second time the request comes in, it goes to node 1, which is not appropriate, right? So because your state of your first node will be completely lost, and then you go to another node. But then again, the way you distribute with vnodes, I'm showing in this picture. So this is without vnodes, you are distributing your hash value, wherein the nodes are directly serving your purpose. You have the ranges distributed. So this particular thing is going to node 1, and vice the similar way, this particular thing is going to node 2. So the way that this issue, or the load issue that I was talking in the other slide, so when a particular node gets affected, it is impacting its immediate neighboring nodes very heavily, right? So if node B goes down, which means all the requests that are coming to serve A, or what is that? Yeah, this is A, B, F, E, F, E. So all the requests that are coming to serve A and F now will lose one particular node. So every request will come to node 1 to serve that purpose, or node 3. So the load on these 2 nodes, the neighboring nodes, when one particular node goes down, is very heavy. Whereas if you see in your second picture, this is where the virtual nodes come in, wherein your data is more distributed, but using multiple hash values, and one particular node is serving multiple ranges on the ring. So if you see node 1, it comes here, and then it serves this. It is spread across the ring, if you see this. And even if this goes down, data is distributed on other nodes in such a way that it doesn't impact a specific node to take the entire load onto it. So that's the purpose of having consistent hashing.
So one maybe a dummy question, right? Like why it is called virtual nodes? It can call data with more nodes, right?
No, this is not an actual node. This is not a physical node that we're talking about. Like I said, this is more of having more hashing functions in between to define it, to distribute the data virtually on a hash string. So this doesn't contain any physical allocation, or it doesn't serve a purpose physically.
Yeah,
So this is just about distributing your servers across the ring to serve more requests.
Okay.
So yeah, basically distributing the hash range of values. So one node will have multiple range of values. So you are using the multiple hash functions, but that is, I think
Yeah, so basically
incorrect.
that node 1 contains those B, G, D, L, like those are what? Like node means, let's say that that is one of the server, right? Like server 1 or something, correct? Like
Yes, node 1 is kind of one server which will accept the B. B is a range of hash function. Suppose like he took an example, right? Like 0 to 25. In reality, the hash values will be of some hexadecimal, which will be, they'll take like last 4 bits of hash function and then use that. Like it depends on you. If you take the whole ring, it will be, let's say it's 65,536 of values. So maybe 0 to 2048, you have certain one node, and then 2048 to 4096, you'll have another node. So I mean, like in this case, one node will have like 3 or 4 such ranges. So B could be defining that 2048 to 4096. E could be defining some other range. B could be defining some other range, like that.
Okay, and here, right, the data which are there in node 1 should be replicated somewhere across other nodes as well, right?
Yeah, we'll come to replication. This is just hashing your values. Replication is a different concept. So we are not talking about.
So here all the whatever you define A to P, these all are unique data set, right? Like in the node 1, node 2, and node 3. I mean to say that, like, so basically, I'm just trying to understand is like, there is a range, right? Let's say that, like if we have, like 65536, then we are just chunking the data, correct? And then in the node 1, we have 2 sets, right? One is in the violet color, MIBF, that is also a similar, basically, like if we are dividing with whatever, like 2000 or 4000 ranges, then we are just saying that, okay, 0 to 2000. Yeah, I know that maybe, like I'll just wait to understand a little bit better, maybe in the later slides.
Yeah, so this is one concept. I think the replication will further clarify. So here he's not talking about, he's only talking about distributing the hash ranges. The replication will ensure the availability. So this does not yet ensure the availability at this point.
Right. Okay. So this is just about how you distribute your requests on a hash ring and load on the servers. Replication will be covered subsequently.
Yeah, so here, right, in the node 1, okay, so basically whatever all the hash ring, that actually we are only thinking about the node 1. Because if I'm seeing the node 2, there also, it's a similar set is getting repeated, right? Like A is repeated in the node 1. So for now, just focus on the node 1. Let's say that we have a replication factor as just 1, right? There is no replication. Right. Then this is what, right? Like there will be a node and all the requests will go there, right? Which will be.
So let's not get confused with replication. So replication is a different concept. This is just about taking the load. So you might be seeing A over here, and A somewhere here. This doesn't mean that this is your replication factor of 3 for all the data. No, that's not how it works. This is just about your token range distribution. That how the servers will adhere to the request serving. We'll go to replication.
Okay.
Yeah. Okay. Any other questions? Okay. Let me move on. So basically, we're talking about. Let's talk about core structure, core components of Cassandra. So we are talking about node. Node is something where you have your basic data stored, or basic database component in which your data is residing upon. So that is a basic node in a hash ring. So the cluster is a group of nodes that are storing the data, and the cluster can be, like I said before, it can be spanning across multiple data centers or a single data center as well, based on how you are serving your requests, whether it is global or multi-regional kind of thing. You can distribute your cluster on multiple data centers. And data center relates to how within a cluster you are grouping your nodes together to resolve your replication purpose. So when we say a data center in Cassandra, you're talking about so when you define replication at a particular data center level or across data center levels, where your cluster can span across multiple data centers as well. But data center will never span across multiple physical locations, which means you're having one data center associated to one physical location, and you might be having multiple nodes in that particular data center, whereas the cluster may span across another physical location which is having nodes from that same cluster as well, and you will be defining replication factor between those two data centers. I will come to replication. I know every concept is taking us back there, but yes, that is where we are talking about replication strategy. So you have multiple strategies that we use in replication. One is simple strategy, where let's say you have this always assumes there is one single data center which has multiple nodes and multiple racks. In that case, it usually goes to a simple strategy that they will be using in order to distribute your data to have a redundant copy of information. So if you see here, in a simple strategy, what it does is, on simple strategy of replication, it goes round robin, takes the request, the client provides a request to the node, the coordinator will distribute that data on the replica in a round robin fashion. So the request goes to the first node, and then it serves in a clockwise, it goes to the next, and then it is returned to the third node accordingly. So that's a plain and simple strategy wherein your request is served based on, no other clauses appended to this. Whereas you have the replication that can be spanning across multiple data centers, or multiple racks we are talking about. So there is something called network topology strategy, wherein in this example, I'm quoting that the data center 1 should have a replication factor of 3, and data center 2 should have a replication factor of 2. So which means you're talking about 1 DC. So you have data center 1 and data center 2, and this has a bunch of nodes over here, whereas this has a bunch of nodes over here. Your write request comes in. You are saying DC1 should have 3, which means this is your coordinator node. It writes your request to 3 different nodes, and then this write also goes to the second data center. It takes the local coordinator, and then it writes the request to two of the nodes. So that's the replication that we are talking about, wherein here the replication factor will become 5. Because you are talking about 3 on one DC and 2 on other DC. So the replication factor will be 5. So here the network topology always replicates the data having the rack awareness. So you, if you know what a rack is something I would define it as that within a particular data center that contains a bunch of nodes together, bunch of servers together. You may have rack 1 containing multiple servers and rack 2 containing multiple servers. And these all might be sitting under the same data center. Now you're saying your replica 1, this particular replica is sitting in rack 1. So one request goes there, and other requests will make sure that you're not hitting the same node, like in the below example, you're not hitting this node while writing your replication to it. So you have 5 nodes over here. 2 of the nodes are sitting in the same rack and another 2 are sitting in the same rack. If you see, being the replication factor 3, it always distributes accordingly that the data is not falling into the same rack as much as possible. So that is another network topology strategy where you will make sure that your availability is distributed across the racks. Also, you have 2 replicas. So there are various strategies over here where you have 2 replicas in each data center or 3 replicas in each data center, like I was talking before. So it distributes the data accordingly on what you're defining your consistency level towards. I think any questions? Hope I'm not complicating things.
No, Ajay, on a quick note, like, will you be able to cover the remaining slides within another 30-40 minutes?
I will try to, Naga. I'll try to cover
Okay.
most of the ground. Yeah, sure.
In the end, we can have some time for questions. So
Sure. Yeah. So I'll first cover consistency levels. I kept the hinted handoff before, but I will go there. So, let me cover this first. So hinted handoff is something where, so like I said, you're writing to multiple replicas over here, right? Let's say you're having a replication factor of 3 and you're writing to 3 nodes. Now, let's say this particular node is down. What happens and how that is handled by Cassandra when you're writing and one specific node goes down. So in that case, what happens is it is trying to write to 3 nodes and one of the node is down. It creates something called hint. So the hints are written locally to the coordinator node, and it keeps the hint by default, it keeps the hint for 3 hours. I don't know, I didn't look at the recent documentation, but it generally keeps the hints for 3 hours in its local. And then it waits for this server to come back. So if this server recovers within 3 hours, then it will automatically takes in that hint and become consistent with R1 and R2. So that is called a hinted handoff, wherein you will set this property to be true if that is how you want to serve your purpose. Any questions on this?
Yeah, so I have a question. So like I was just trying to, relate it with the MySQL as well. So in MySQL, we have something like write ahead logs. So whenever we are writing, right? So first it is written to write ahead log, and then it is, persisted to the actual disk. So the hinted system hints basically, is it similar to the write ahead logs or like something different?
I am not quite sure.
I can take that.
You want to, yeah.
So write ahead logs are mainly meant for durability. So which means that once you write data, in RDBMS, it needs to guarantee the durability, right? Acid properties. So here the idea is like you already have the same data in node 1 and node 2 already, but the main thing which you are trying to guarantee using the hinted handoff is a replication factor of 3. So in the beginning, for any type of table, like or like any particular database, like when you define a replication factor 3, it means that you are guaranteeing at least 3 copies of those in different nodes of the same data. So in this case, the 3 nodes which were designated to store certain hash range. So like in this case, let's assume like 0 to 128. If it's 0 to 64, all of these 3 nodes are there, right? So the R3 was meant to store like this copy, but it wasn't available. So as a temporarily, like it's just like if you imagine if you are locked out in your house and you are temporarily sitting in your neighbor's house till you find or till you get the lockman, figure out how to open your home, something like that. So it's temporarily the data gets parked onto node 4 while the R3 node becomes available. As soon as R3 becomes available, the node 4 will pass all those system hints, which is the data which is supposed to be stored by R3 to that node. So it can happen with any other nodes as well. So this is just an extra layer of availability and guarantees. So using the hinted.
Naga, would it be right to say that this approach, hinted handoff, is more like to handle failure, right? And how to
Yes, correct.
code and replication, whereas write ahead log is more for durability and performance, right? You don't want to
Yes.
be writing to the disk with every small write. So yeah, okay.
Yeah, this is this Cassandra uses that leaderless quorums approach, which I have discussed in the past, right? So it is this is one of the technique to increase the. I think this is to handle the failures basically. So temporarily now
Yeah.
R3 got failed, and you're handling that failure temporarily by writing to a neighbor node, or like in this case the coordinator node, which will hand off the data as soon as that node becomes available. It's kind of one of the failure tolerant techniques in case if somebody asks you in an interview. So this is one of the good technique to bring it up.
Yeah, right, Naga. I think you have answered my question, but I have another question on top of that. So let's say R3 is like node 3 is down, right? So replication has not yet happened, right? Which is the R3. So what if that node 3 is, let's say, take, let's say 10 minutes to come up, right? It's just a hypothetical time. And node 4 goes down at t equal to 5 minutes. Now what happens?
No. When node 4 comes back again, it will hand off the data. So you still have that data in other nodes. Like whenever this node 4 comes back, only then it can hand off the data, right? So
you're talking about a situation where node 4 also goes down, which means so this is just an optional thing. So if node 4 goes down, you will still have your data in the other nodes, and you have concepts like read, repair, etc., which will cover your other nodes recovery based on the other concepts that we're talking about. This is just about so if this node recovers within the configured time, then these requests will be served from coordinator node. In any other scenario where either node 4 goes down or node 3 doesn't come up, it is always recovered based on the other recovering solutions. I'll come to read repair in a few minutes.
Okay. I'll wait for that explanation.
Yeah.
Thank you. Thanks, Naga.
No problem.
So I was talking about consistency levels. There are various consistency levels that you define at a write thing and a read thing. So when you say so these are different things. So any is something where you're talking about, okay, now you wrote to multiple nodes and you are okay with if the write completes at least in any of the nodes that you're defining. You might be having multiple data centers, you might be having a single cluster with just 2 nodes and one of the nodes responds to you. You're fine with it, then you will be going with any, but generally it is not recommended to use any as your solution that you're talking about. It only corresponds to a single replica, and a coordinator may store a hint, and if the hint stored, the coordinator will, if the hint is stored, the coordinator will try to attempt to replay the hint again and deliver the mutations to the replica. But this is not an acceptable replication to be used in a production system unless you have a very specific. The more recommended approach is to use one or local one kind of consistencies, because that will guarantee you that will at least make sure that you have one defined recovery solution over there. Whereas you have quorum is something where you are defining a replication factor of 3. Then you are talking about 3 by 2 plus 1, which is this will be like so 3 by 2 will always take it as 1. 1 plus 1 is 2. So it takes 2 as your. So when you get a request, while it is serving your request, it will make sure that the acknowledgement should come from. So if you're writing to 3 nodes, it will make sure that 2 of the nodes should actually respond to you saying, okay, I'm okay with this write, and only then it will go to the client and says, okay, I'm fine, I got the quorum. So are you clear with this?
You can proceed.
So the serial consistency is something where you want that to be executed only in a specific order. Like after writing to one node, you go to the next one and then write and then go to the next one. So this includes a lot of overhead of back and forth protocols that are running between, and it has it is not always used in a regular kind of system. So so this is a very lightweight transaction, but eventually it adheres to a quorum underneath, and also it makes sure that the execution is happening in one after another sequential order. So if the links go down at some point, it will. So let's say you have multiple data centers that you're using. If you're using a serial as your quorum, serial as your consistency level, the amount of time it takes to give you a response will be a very slow operation, as it includes a minimum of 4 times more round trips between the requests, causing the sequential execution of the request. So that is where serial execution is not so preferred unless you have a very specific use case where you want to write it in a sequential manner. Okay, and local one or local quorum, when we say local, you're talking about having multiple data centers and your request should be served. The response should be based on that, okay, I get a quorum from only the current local data centers and I'm good. Then that is where the local keyword comes in. 2 and 3 are having a response from 2 of the nodes or 3 of the nodes will serve your purpose, is when you will be defining those consistency levels all is the most slowest consistency level, where let's say you have two data centers with replication factor of so with read consistency level of 9. So which means you are talking about having all the nodes from each data center respond to you on every request that you're giving. So that is like you're talking about a latency factor which is slower than your MySQL single node machine. Yes. Okay, I will quickly cover the other topics and then we can see.
Before going to that, about the local quorum formula, I guess there needs to be some correction. The formula should be like the sum of write consistency and read consistency should be greater than replication factor.
No.
So you can,
quorum,
yeah.
Quorum, local quorum is defined for each, right? So it will be either for write or for read.
No.
So
You can define it separately, like read and write.
Yeah. So these are defined separately. This is not like so you have local quorum on write as well as read. So it is always like read factor, replication factor divided by 2 plus 1. So I didn't get your. So it is always the majority when you say quorum. It is always the majority of the nodes, right? So
Okay,
let's say.
Yeah, go ahead.
Let's discuss this towards the end, if otherwise.
Okay. Meanwhile, I'll try to come up with a scenario.
Yeah.
So
you come up with a scenario and post it in chat. Like, let's bring it up and discuss towards the end.
Sure.
Just to make sure we cover.
So quick thing. Let's say you have 3 data centers. You have 3 nodes each on each data center. What would be the quorum? The quorum would be 5, right? Because you're talking about 9 nodes, and it should always be greater than 9 by 2 plus 1. So it is the majority that we are taking in here. So anyway, we'll discuss later. But so yeah, I'm giving a basic difference between a relational table and a column family. So in relational table, everything is fixed, right? So you will have a set of columns, and then you can write. So the schema is defined, and you will be loading the data into that particular schema, and you will at least keep a null value into the column. Whereas in Cassandra, you can add a column at any point of time, and it will still adhere to your request. So your row doesn't need to contain a column which has a null value within it. So you understand my point, right? So if you add column to MySQL, let's say, and you don't have any data, all the values that particular column contains is all null, but null is still a value that is stored in your database. Whereas in Cassandra, your rows can have varying structure of columns, and anytime you can freely add the columns into the column family. Okay, let me jump on to other stuff probably more quickly. So I'm defining how the rows and columns are defined over here. So the key space is something which is an outermost container of all your data. You can associate it to something like a database in your relational system. And a column family or a table is associated to something like a table in your RDBMS system. So in RDBMS system, row is an individual record that you're talking about, whereas in Cassandra, you're talking about row as a unit of replication. So the way you replicate your Cassandra data is where your row concept comes into picture. Whereas entire storage of your Cassandra will still be at a unit of a column level. It is not stored like in your RDBMS system. It is not stored as a row-based value, wherein your values are stored in pages and it is retrieved based on your rows. Also in RDBMS, you have concept of joins, which I covered joins in your RDBMS, but whereas in your Cassandra system, you will have collections, like you will have a particular column family adhering to a specific query request that I was talking about earlier. So there is no relationship of joins as you see in your RDBMS system. So here I'm talking about row keys. I'll skip this slide for now, which are associated to columns. But if you see, the row key 1 is differently structured from row key 2, whereas your column 1 will still stay the same. So this is like your varying structure of your columns, where you are adding columns to an existing column family, where your data doesn't need to be stored as nulls or something. The other key concepts, I'll run through next 3 slides a little faster, but those are the most important concepts. So I want to make sure I'm covering those before we jump on to questions. So we have 3 important structures that we use in Cassandra. One is commit logs, wherein they are like append-only logs with all the mutations stored to a Cassandra node. So any data written to Cassandra will be first written to a commit log before it is being written to a mem table. This provides you the durability on an unexpected failure. Now, coming to what is mem table? Mem table is like a memory structure. It is stored in RAM, where it resembles a write back cache. So when a write request comes in, it stores in 2 structures. One is commit log and other one is mem table. Commit log is on the disk, whereas mem table is in memory. Commit log is something that, so if you see the structure, so commit log is something that is persisted on a disk, whereas mem table is something that is on a memory. So also the difference between these two is commit log writes, like I said, it is an append-only log. So however order that you are receiving your data, that will be stored in the same order in the commit log. Whereas on your mem table, your data is sorted accordingly based on your final storage of your partition keys. So mem table is more of a sorted structure, which eventually flushes into an SS table, which is on a disk. So SS table is something that is an immutable sorted string table, sorted string structure, which is stored based on your partition keys. So there, the flush of mem tables to the disk happens on 2 factors mainly. One is the time, the other one is the size. So the time, it can be bound to, okay, after a certain period of time, I need to flush this data based on your configuration. Or if your commit log or mem table size grows heavily, you may flush that data as well to your SS table. Now, writing to SS table is not like a sequential write that you're doing and leaving it at one place. There is a concept called compaction, where the writes will happen continuously and then eventually it does a compaction. So when you get a delete request, so what happens in Cassandra is it associates a tombstone to it and writes an entry to this. So the record that already exists on a previous SS table with a specific value will still be present in that SS table, while there is one more SS table with the same adhering to that partition key, which is containing that tombstone. So the compaction is the process where it takes both the values and provides you the final value based on more recent information or more recent timestamps. Any question on this?
To add to that, this compaction is so every node has a threshold of the number of SS table that needs to be stored. So when the threshold reaches the node, the Cassandra, it triggers that compaction process where it combines multiple SS table into a single SS table by replacing the replacing the recent record in the SS table and deleting the old ones.
So yeah, this is one of the slides. So if you see on your left, you have two SS tables. So one is having older timestamps, one is having a newer set of timestamps. So Johnny is having the same value, nothing changed after a timestamp. So it gets stored on a compacted SS table as the same value, whereas Betsy is something that got deleted. X is like your tombstone. So X got deleted in the second SS table. So you don't see that value in your final SS table after compaction. Whereas number 3, you see that this value got updated, which means it takes the more recent timestamp for number 3 and it writes normal onto the final SS table. And also there is something called grace seconds, GC grace seconds that are associated to tombstamps. These are used for recovery or rollback kind of situations, whereas the tombstamp of 5 is still retained on the final compact table because the GC grace seconds that you defined for a deletion didn't exceed the value. So that is how actually compaction works.
I have a question on compaction here. So in somebody, I don't know if it was Vignesh or someone, but there was this mention about size tiered compaction, right? Like when we are saying when the size of SS tables grows beyond a threshold, then it triggers and it tries to run compaction. Do you also know anything about? I have heard this term called level tiered compaction, but I'm not very sure what that means. Does anyone here have an idea about that?
No, from what I read, so it is not about the size of SS table, it is about the number of SS tables in a node.
Okay. So that is one. Okay, so number of SS tables. Yeah, my question is coming more from, it's kind of a random one, but yeah, just the book club, we are reading the same thing. And we had this question today that what is level tiered compaction? So, okay, that's fine. Maybe I need to go and check.
I think Cassandra, they are using only size tiered compaction.
So actually they mentioned in one of the blogs that Cassandra introduced level tiered also to address the limitations of size tiered. But yeah, I don't know much about it.
Yeah, even I'm not.
Good idea. I mean, thanks.
Yeah, you use node tool. That's one of the utilities that you will be using to execute some of these administrative kind of executions. So let me go back to SS table. So now let's go to a read path quickly. So when a read request comes in, it first checks something called a Bloom filter data structure, wherein that's a rapidly efficient or memory efficient data structure, which just tells you, it doesn't guarantee you that SS table contains it or might not contain it, but it's a probabilistic data structure where your output is whether the data is present or not in a probabilistic way. So you can check the Bloom filter. If it says yes, it is not certain that it is always present in your final structure, but most of the time it is more than 90% guaranteed that the data exists in the Bloom filter. That is one of the concepts where you can go through, and very cool concept to learn as a data structure. So once it goes through Bloom filter, it checks it's partition key cache. Partition key cache is something where your recent reads are stored into a key cache where if it exists, it directly goes to its offset and fetches that data. If it doesn't exist in a key cache, then it should go through a path of going to a partition summary, checking for its index, and then go to partition index, get the offset, and then read the data. So the partition key cache or partition summary and Bloom filter, these are stored in memory, whereas partition index and the respective data is stored in disk. So this is one of the samples where you see the bottom is the access table, wherein you have the offsets defined for each partition key token. So the request comes in, it is checking the key cache, it is finding 36, and it just goes to that particular offset and fetches that data and serves the purpose of that read. If it doesn't find 36, let's say it gets something in 20 or something, and it particularly goes to that particular token in, this is the partition summary that we are talking about, wherein it goes to that particular partition summary, and it goes to the offsets that are defined to that particular index, and it goes to the respective the corresponding values on the SS table. That is the second path that we are talking about. Any questions? Okay. So on the there are few concepts around how the reads are served in a much better way. So you are talking about eliminating the keys by eliminating the values by keys. So there is a so the metadata maintains a minimum key and maximum key on an SS table. So if the key is not falling in that range, it will eliminate that SS table to be checked for a specific value. That is one way of eliminating the SS table. The second thing is Bloom filters, like I was talking about. It goes to that particular Bloom filter. If it says no, it's for sure it is not there. If it says yes or probably not, then it's where the probabilistic response comes in. Maybe I'm a little confusing over here, but yeah. There is elimination of clustered keys as well, wherein your request comes by a set of clustering keys. Then the SS. So what we are talking about is on a node, you will have a bunch of SS tables sitting, and reading through each SS table to find a specific value will be very time consuming. So there are these layers that they keep over that just to make sure you eliminate most of the SS tables and go to the respective offset more quickly. So this is a mem table read wherein you're getting a particular token. So the data in mem table is always sorted as per it is trying to store into the final SS table. So it is always quick read that you will get out of a mem table, where you will go to that respective token and fetch your data that you're trying to look for. And then I think these concepts I can skip. This is a driver which is trying to serve your purpose. On drivers, so driver is something that you will have a JDBC driver or whatever driver that serves you to connect to the Cassandra cluster. Will have certain policies to load balance your request. So one is DC aware policy, wherein, for example, your all your nodes on your local DC is down. So it knows that the request should be served from DC2. So that is called a DC aware policy, wherein it generally goes by round robin, and generally it is aware of its local DC, and then it checks on its local DC. If all the nodes are down, then it goes to the second data center and serve your request from there. it is generally in a round robin fashion that it happens.
Is that
So,
sorry, is that provided that replica is on a different DC, right? But it's the
yes,
way they set up the replication, it need not be.
it may not be. Yeah, that is true. Provided the replica is maintained on both the data centers. Yes.
Or I was wondering, like, is it for the BCDR kind of setup, or is there no concept of BCDR in Cassandra? Because you can replicate to multiple data centers, so that's already taken care as part of replication.
Yeah, you're talking about disaster recovery concepts. No, generally your configurations will take care of replicating to multiple data centers, right? So
there's no disaster recovery.
Yeah.
Kind.
Yeah.
Okay.
So you will have your consistency levels defined. So all your requests will adhere to a specific consistency level. If there is no adherence, then so unless it reaches a quorum or the consistency level that you define, it doesn't commit to that particular value as present, right? So.
Okay. Thank you. Yeah.
So while preparing this request response, there is a phase of prepare phase where it first goes to the coordinator with the query that it is trying to send, and it receives a statement ID and metadata with respect to that statement ID, which includes the partition key as well for the query that the driver is requesting. So this is a prepare phase for token aware policy. So while you're serving your load balancing using a token aware policy, it already gets the metadata from a coordinator node first. So the prepare phase can happen on multiple nodes. It's not that it goes on one single node. So your driver might connect to 2-3 nodes at a time, and then this does a prepare. It gets the metadata back, and then it sends the request based on your partition key that you are receiving out of the metadata. So that is where the token aware partition key comes in. So you know the partition key based on the hashing that you did on the prepare phase, and then you will go to that respective distributed hash table, go to the corresponding node and fetch your response to the request that you are getting. Okay, now coming to the coordinator node, there are few things that we are talking about: read repair and latency awareness. So basically, the coordinator will have a few factors to consider on how to serve, whom to request the thing. So it will be aware of the data center on which it is requesting. Also, it will be aware of the node liveness and amount of latency that is happening between the nodes. So if you see, this is 1, 2, 3. We're talking about latency of 20 on one of the nodes and 2 and 1 milliseconds on the other two nodes. What it does is it takes the data request and sends it to the least latency value, and then it sends the digest request to the second node. So the data request is something that serves your request, whereas the digest request is something that validates your response that you're getting from other replicas. So that is where it compares both in memory. It makes sure that it is getting consistent results if the quorum is adhered, or if the consistency level is adhered, it goes to the client and responds to the request. Let's say you have two different results coming out of these two, data and the digest request. Then it knows that this is of timestamp 10 and this is of timestamp 30, which means this is a more recent information that it is receiving from this particular node. Then it initiates a read repair on the second node that it is receiving data from. So this is where it collects the, so there is a gossip protocol that will be happening, and also there are concepts like dynamic snitch, which also adhere to or serve to the purpose of this whole process of coordinator doing the read repairs or serving the requests on top of the regular flow. So I covered the compaction. So yeah, just quickly on the gossip protocol. So each node learns the topology of the cluster, and it keeps communicating with the other nodes with a broadcast protocol for making sure that the peer nodes are available, and the health of those nodes are tracked continuously between the peer nodes, eliminating a factor in to have a master node on top of it. This brings the decentralization of peer nodes. There is no one single server which will be making sure every node is up or one node is down kind of thing. So we are talking about epidemic. We are aware of epidemic these days more than ever. I will show that into this picture. If you see, it starts with 2 nodes, and then each node is learning about all the other nodes based on the information that it is receiving from the peer nodes that it is getting in this protocol. So what does the gossip actually contain that the nodes are getting aware of the situations? The data structure contains a heartbeat, wherein it periodically monitors the incrementing value that it is receiving from the other node, just to make sure that a value is so if the value is not incrementing after a certain period, that means that that particular node is dead, right? And it also has a state of application that is maintained underneath, which contains what is the load, what is the severity of any pressure that it is receiving, what state it is. Like when a node is so there are various states of a particular node. It is bootstrapping, or it is in a hibernate mode, it's normal, or it is leaving, left or removed. So these are self-understanding, but that status gives the protocol, gives the gossip that information that, okay, that this particular node is leaving, so the request cannot be served by that particular node. So that whole state of that information will be served in the gossip protocol. Also, it will be aware of what rack this node is in, or what DC this particular node is in. So this is basically defining your state of each node and distributing it across all the nodes in the ring, just to make sure you are having all the nodes up, or if there is a read repair or anything that is required, will be served from that purpose. I will not go into these details. There are certain things like an initiator will initiate a request, and then the peer will receive the request and takes a diff of it. Diff is something where it goes to it identifies 2 things. One is what does it have? What does the new initiator have that this particular node is not having? And also, what are the states of what is the state of the initiator that it is receiving? Based on that, it sends an acknowledgement back, and then the initiator will send an act to the peer node. So this is the whole protocol of the gossip that we are talking about. There are a few other terms like snitch, which I didn't dive deep into. So snitch is about your network protocol. So it spreads, it allows Cassandra to spread the replicas around your cluster to avoid any correlated failures. Key space we already covered. That's nothing but a database. So yeah, I think I'm done with my session. Any questions?
We still have 15 minutes. First of all, thank you, Jay, for taking this session. It was, yeah, definitely very informative. And
Yeah,
I hope.
I'm sorry, guys. I never gave a session to such a large audience, so I'm definitely more.
No, this is a good one. It's a pretty good start. And yeah, open for questions, and we have about 15 minutes. So Ajay or like even others, we can start.
So yeah, I have a question that you mentioned when we write, and then we need to get the replication factor, right? And then let's say, if we cannot meet with the replication factor, how do we roll back the data? Because some of the node already have that new data. Does it make sense, my question?
I didn't understand. So you said the replication factor.
So yeah, let's say I have replicate factor of 3, right? Mm-hmm. So I need to write, to 3 node.
Yes.
Same value to 3 node, but now, I able to write only 2 node. The third node I'm unable to, and I need to roll it back, right? How do I roll it back?
Oh, okay. You mean to say, like, if you are not using like hinted handoff and you are doing a strict, I mean, like you can't reach certain, you can't meet the replication factor, and you want to.
He's talking about the rollback when the replication factor is not able to
succeed. Okay.
So,
I think. Yeah. Go ahead, Vignesh.
Yeah. I think so. There is no rollback in Cassandra. So as the presenter said, there is something called hinted handoff. So there will be hints that will be gathered by the coordinator node, and so it has a time limit of 3 hours maximum. So once it is not, the node is not up within the given time, it will be flushed. It will be thrown away. The hint will be gone. So at the time of read, at the time of read, there is something called read repair, which he just explained. So if the hinted handoff is missed, the read repair at the time of read repair, the data will be fixed.
Then during that time, when query for the same data, does it return the old data or the new data? And how does the the node get updated? Know that it should not use the new data because it's not consistent through 3 nodes.
Basically, that's what like he's talking about, the read repair. Like coordinator will query 3 nodes, and it will find that 2 nodes have the latest data. 1 node is having the stale data, but
he say the read repair will kick in after 3 hours, right? Is that right, or is that like right away?
Yeah,
no, see, the read parts actually.
If the down node, if the dead node misses the hinted handoff, so it has to wait till the read repair occurs. Otherwise, it will not know whether the update has happened or not.
So, so the Cassandra, to answer that question, so Cassandra will not have, so there's nothing called rollback or anything, but if you don't receive the consistency level for the write, so the defined consistency level, it will respond to the client saying the consistency level is not met and write got failed.
Okay, so but the coordinator node have to tell node 1 to say, okay, don't serve that
discard this data.
Yeah, discard it somehow.
Yeah, that will be like a tombstone concept, right? So it will mark the current writes to mark a tombstone against the writes that happened in that transaction, and the further transactions will not refer to those rows. So if you see in this node, you're talking about, this might be a delete statement, or it can be a write back statement, right? So I believe that whatever rollback that happened will associate a tombstone to the partial writes that happen, so that they won't reflect in the further transactions that are trying to read that same data.
Okay, but what if like this data is like you modify the data, not the new data, but you modify the data, and now you put the tombstone in here? That would mean we delete the data instead of use the previous one.
Yeah.
Yeah, that's right.
I think probably we should look into it. I didn't think in those terms. Anyone can answer them.
It is up to the application to handle. I mean, if you are facing a write failure, I mean, you should retry or something like that. But Cassandra doesn't have any rollback strategy as such. I mean, it can get auto repaired, as people have said, I mean, by the read repair thing. But Cassandra doesn't say anything that if a write has failed, it will clear the old ones as well. It is up to the application to handle.
Yeah, and the Kafka also follows the same style. You can decide whether you want to meet the quorum or you want to meet the 2 instances. So unless that condition is met, the database does not return you a successful response. So if you don't get that successful response, it means that the database has failed to do that and you can retry. Or else database will give you that successful response only when whatever condition that you have specified is met. So there is like a guarantee from the database side.
But the database, I mean, the client doesn't know that, the node 1 and node 2, get updated data and doesn't even know the address of node 1 and node 2. How would the client, tell node 1 or node 2 to discard that value?
I think we are talking about the writes, right?
Right.
Yes. So the the Kafka, the database will only return when it has met the condition that we have specified. Else the database will not return you successful response.
I mean, like response is okay. I mean, like the concept is like because of the replication factor P, it's partially returned to some nodes and not returned to all the nodes as expected by the client. So that's where it's returning the failure. But what will happen to the nodes where it's already returned? Is coordinator going to send a ignore or like tombstone request asking to ignore, or
So,
like is it simply like lying there and not serving?
You get a message saying that consistency cannot be met. I mean, that is up to the
Yeah, I
application to
assume like
ensure.
the coordinator takes care of discarding, because if it doesn't get the required consistency level, I think internally it's going to discard or like yeah, but like maybe we can take this question and probably look inside, look further to understand. Any other questions in the interest of time?
So one question that I have is, I think we discussed that this is a highly available system. So multiple nodes also can take the writes, right? So if there is a conflict between 2 values, how does the Cassandra resolves it? Is it like the last write wins, or?
Yeah, I think, yeah. So an example of a conflict, can you give? I think the maybe the times.
No, it's last rate wins only, because it solely depends upon the timestamp of each record. Even if your data modeling, you must to give the timestamp. Cassandra internally happens timestamp to each of the data that is writing.
If you don't maintain the timestamps correctly, in that case, like you may have some issues there. But like, yeah, but like I think that's a default strategy of Cassandra also.
So there is one more misconception about Cassandra, like as it so much depends on ordering and timestamp, and it's a very well-built heavy write machine. Some people thought of using it as queues in place of Kafka kind of thing. But that is not suggested. But yeah, just bringing in that thought.
Mm-hmm. Any other questions?
Yeah, one thing I don't understand about that consistent hashing. If we already have consistent hashing, why we still need the request go through the coordinator? Wouldn't that we just hash the request
because of the
ID?
replication factor and the consistency targets, right? Like one of them will act as a, it's not that like if replication factor is 3, client asks the client whoever is writing to talk to all the nodes individually and wait for response. So one of the node tends to act as a coordinator. So though you have this ring fashion.
But then, okay, so the request, how does we need to route the request to the right coordinator? Is that based on the hashing?
Any node can be the coordinator. So I think folks correct me.
Yeah. Each node has the each node has the data of all other nodes. No, each node knows what this particular hash and where this particular hash needs to be sent to. So it will act accordingly.
That's right. There is no specific role called coordinator. The coordinator is picked by the driver. So the driver will be aware of its nearest cluster that is available, and it picks one of the nodes in a round robin fashion from that local cluster and sends the request.
Okay. Any more
if you see in this prepare phase, if you're talking about, so the first thing that it does is it goes to the nearest request, nearest node that is available, and it requests for a metadata, and then it goes to the respective nodes having if you are using a token aware policy. If you're not using a token aware policy, then it will take one of the coordinator nodes as its coordinator and passes the request to it. So the driver plays a very key role in picking the respective coordinator always. And coordinator is not a defined node, but it can be any node within the cluster.
Yes.
Okay, one last question I have. So this coordinator node is there, right? So whenever a request comes and it kind of hashes the request ID and then knows the hash value and then it knows which node to talk to. But what about the replication factors? Because so let's say there is a replication factor of 3 and the 3 nodes has this data, and the 2 of the nodes might not hash it to the particular the request ID, right? But I don't know how the replicated nodes are being tracked for the particular request.
It depends on the hash change, right? Oh, you mean the replication factor? Okay.
Replicated nodes, yeah.
I think it should be there on the configuration somehow.
So this is where this is what I was missing in my analysis of Cassandra.
Basically, this partition key, when you define your table like or column family, whatever, when you define the replication factor, right?
Yes.
So,
yes, yeah.
So any data that you are storing for that table or node, so all those keys will definitely need to adhere to that replication factor.
But how does let's say request of ID 1 comes and it is getting hashed to node of 3, right? And it is being sent to node 3 for a write, and it needs to be replicated to 2 other nodes. How these 2 other nodes are selected? It is like random.
So they were round robin. They were round robin. In the request, it always goes round robin. it picks the first node, it writes to that, and it picks the corresponding two nodes in a round robin fashion.
Oh.
And it is again configurable, like Naga said, but generally by default it goes round robin.
Maybe I think it's a different way. I'm not sure. So basically, in consistent hashing, whenever you, without the vnode concept, so you hash it to a particular node, and for the replication, you generally add it to the next immediate nodes itself. If replication factor is 3, and if the selected node is A, so you add it to BC nodes itself.
Right.
So similarly,
so that is
yeah.
It's a good point.
Yeah. Similarly for that, token range, you select that next node itself.
Okay. It's nice. It's a nice thought. Okay. Thanks for the.
But in that case, isn't all the nodes will be fall into the within the same hash string? Let's say that we are writing to node 75, and the next one is 76 and 77, right? So what will happen if that entire, again, it depends on which DC those are, right? Because the replication has to happen in cross DC. Otherwise, there is no concept of availability, right? So
it is in the same DC as well as across DC as well. Replication factor is for every DC.
Yeah. The quorum, through the quorum you can define. If you define as local quorum, it is particular
within
DC.
the DC, right? Okay.
If you define the quorum as quorum, it is across DC.
Okay. So again, it has to select some of the nodes in the other DC, and it has to.
Yes.
Makes sense. Yeah, I believe that might be a configuration. Okay.
Yeah. So always the read for the read replication, the local quorum is preferred because it needs to wait for the other data centers nodes to have the data, right? So always
that makes sense.
Have local quorum for read replication.
So if you see in this example, I was giving you multiple data centers, and it is having replication factor for each data center. So it's like you will define it specific to the DC, like someone is saying. Yeah.
So this is for read or write replication. Like 3 means both read and write replication, or
no, replication is always right?
Right.
So you will take number of copies. So you are confusing between consistency level and replication. So the replication is always the number of redundant copies that you are keeping. So in DC1, it keeps 3 redundant copies in this example, whereas in DC2, it keeps 2 redundant copies.
Correct. And whenever the read happens, it goes to the nearest DC. Let's say that, it is DC1, and then it has to, let's say that we wanted to make sure that, don't just go to one node and fetch the data. It has to be.
So that is where the consistency level comes in. So if you define consistency level as 1 or 2, it just goes, takes the response from, takes the confirmation from 1 or 2 nodes and comes back. Whereas if you define it as a quorum, the consistency level will follow the respective configuration that we're talking about.
I see. Okay, makes sense.
Yeah, so that's where the local quorum and quorum comes into picture. So local quorum is for particular DC and quorum is for across DC.
Correct. Yeah, and you have to decide, right? Like how fast you want these reads.
Yes.
Otherwise, if you go to entire, if you have 10, 15 DCs like Facebook, maybe hundreds of DC, then you are really losing the read, timing, correct? Yeah.
That's true. As the number of as stringent you are with consistency, the latency also increases proportionately.
Yeah.
Okay, I think we are almost over time, over a few minutes. If there are any other questions, please ping it in the Discord channel. And Ajay, feel free to share this presentation in there as well.
Sure, Naga. I'll post it. Yeah.
Okay, and let me stop recording, and I have one more thing to say.